Good morning, everyone. Thank you for being here for our session today, Scalable High-Throughput Electrocatalyst Screening. My name is Andrei Linka. I am content creator for VSPARTICLE, and today I will co-host this session together with my colleague Katarina Weber, who's going to do the Q&A session. The presentation today is provided by Dr. Klaas-Jan Schouten, who is a researcher at Avantium and a part-time assistant professor at the University of Amsterdam. Klaas-Jan Schouten's presentation was initially broadcasted with Material Pioneers. For those who don't know, Material Pioneers is a community that wants to create a new way of collaboration, resources, and infrastructure to support scientists and researchers in the effort to discover, manufacture, and develop new materials. You can find more information on their website at www.materialpioneers.com. The Q&A session, as I said, will be handled by Dr. Katarina Weber, who's a researcher scientist at our company. Before we dive deep into the presentation, I would like to take you through today's agenda. We will discuss handling questions during the presentation, webinar recording. I will then give you some information about upcoming events, some information of how you can get in contact with us and request additional information. I will then provide you with a short introduction about VSPARTICLE, and then we will move on to the recorded presentation. The last part of this session will handle the answering questions. We are taking questions during the webinar and we'll try to answer all of them after the presentation has ended. You can find the chat room in your bottom right corner, the icon with the question mark. Please don't forget that during the session you are on mute and you won't be able to speak. So for feedback, comments, and questions, please use the chat room. The webinar session will be recorded and we will send you a link in the coming days so you can share it with your colleagues or watch it later. We have two upcoming events. The first upcoming one is on the 11th of March 2021 at our regular time, 10 a.m. and 5 p.m. for China and 6 o'clock for Japan. The event is Nanoparticle Generation with VSPARTICLE Spark Ablation Tools, presented by Andreas Schmid-Ott, which is the co-founder of VSPARTICLE and Spark Ablation Technology Pioneer. And to be announced is the VSP-P1 Nanostructured Material Printer, a product demo webinar. There are multiple ways in which you can get in contact with us. If you would like to know more about VSPARTICLE solutions and how they can help you in speeding up your research, you can always check our application notes at www.vsparticle.com/applications. Or if you would like to try the VSPARTICLE technology in the safety of your own lab, you can request a free demo via a form available at www.vsparticle.com or by email demo@vsparticle.com. For any other questions and inquiries, you can always contact our sales team, sales@vsparticle.com. VSPARTICLE is a spin-off company of TU Delft in the Netherlands with over 20 years of experience in the synthesis of aerosols. And with the help of a young and passionate team of scientists, VSP is unlocking a whole new world of possibilities at the nanoscale. We develop and commercialize a completely new technology to automate the production of new materials, and we are key nanotechnology providers in different industries like semicon, catalysis, and health. Since 2014, we have helped scientists and industry leaders around the world drastically reduce the development time of new materials and products by enabling automated nanoparticle production. And here you can see a layout of our current product portfolio. Thank you for waiting with me through this introduction. I will now go through to Jan's presentation, and I will talk to you at the end of the presentation when Katarina will take your questions and we will proceed to answering them. Talk in a bit and enjoy.
Avantium. Actually, 4 days a week I work for Avantium, and 1 day a week I work for the University of Amsterdam, because I really want to bring science and business together to accelerate electrochemistry, because that's my expertise. I'm an electrochemist. So first, a brief introduction of Avantium. So Avantium has 3 business units. At the bottom, you see the business unit is called Catalysis. And what we do there is that we offer systems and services for catalysis research. It's mainly heterogeneous catalysis. And we do that for a range of clients. And I will talk later about what they do in this business unit, because actually their core expertise is high throughput catalysis research. Now at the top left, you see renewable polymers. And what we do there is we develop technology to convert sugars into polymers. So we make bio-based polymers. And the first plant, commercial plant for that, will be built actually in the Netherlands, in Delfzijl. We already have a pilot plant for that in the south of the Netherlands, in Geleen. And then the last business unit, where I'm in myself, is renewable chemistries. And there we have 3 programs. The DAWN technology to convert non-food biomass, such as wood residues, into industrial sugars. That's the DAWN program. We have our here called Mekong program. Actually, the most recent name is RAY, the RAY technology. There we convert sugars into plant-based monoethylene glycol that you also need to make bio-based polymers. And the last technology, actually where I am responsible for, is the Volta technology. And there we convert CO2 to chemicals using electrochemistry. And also there we use high throughput catalysis developments. So that's also what I will talk about. So first I will talk about catalysis, so the business unit at the bottom. And then the second part I will talk about Volta. And so catalysis is our business unit where we offer systems, so you can buy those to do your own research, or services, and then we do the work for you and you get the results in the area of high throughput catalyst testing. Now, why actually would you want to do high throughput research? Now, for example, for a project, for a client, we tested 600 different catalysts and only 2 of them actually worked. So if you would have to test them one by one, even if it would take only a day, it would take 2 years to find those 2 hits. So this really shows that if you want to find a new catalyst for a new reaction, you need a high throughput approach. But there are also other areas or research goals where you also need high throughput. I will show those in the examples that I will come back later. So first, one slide about what is high throughput catalysis research and where are we today? Now, sometimes people think of high throughput research as it's just a like quick and dirty way to see if it works or if it doesn't work. Well, maybe that used to be high throughput research a long time ago, but today that is certainly not. It's not a quick and dirty experiment to see which catalyst is working. Because today, what we can do with high throughput catalysis research is really look at real feedstocks, real industrial catalysts. Avantium has a whole library of thousands of industrial catalysts, so we can test them. We can also test them under realistic conditions, both for, let's say, early stage development, but also really to find this 1 or 2% extra reactivity to optimize your process. Now, in all those cases, you really, it's not just that you do a high throughput catalyst test and that's it. No, you really need, from the start, make an experimental design. So now I go to the circle on the left. You have an idea that you want to test to make an experimental design. Then you do a very well thought of catalyst synthesis or catalyst selection. Then you need to do like a very thorough and well-controlled catalyst testing. Then you get a lot of data, which you need to model. And then you can validate your idea and then repeat the cycle. So data analysis is really crucial in high throughput research, and also actually your analytics. So the analysis of the products, the byproducts, decomposition products, everything you need to be able to analyze very thoroughly to do a proper high throughput approach. Now, in Avantium, we have two general technologies. So one are batch reactors. You see that at the right. So we can do up to 72 small autoclave reactors in parallel. Or we can do a continuous reaction, and that's really the industrial conditions. And that's fixed batch reactors, and then we can test up to 62 reactors in parallel. And then I go to the next slide. So I'm going to show you some examples of how we have used this technology. And those examples are from two different reactions. So at the left, you see the oxidative coupling of methane. So we go from a C1 molecule, 1 carbon, to a C2 product. So at the top left, we really did a catalyst screening. So we looked for many, many different catalysts to see which one is the best, which combination of metals, for example, would be the best. So what you see here in the plots is on the x-axis, the methane conversion, and on the y-axis for the left plot, the selectivity to a C2 product. So there you actually get the methane coupling. And for the right plot, it's methane conversion plotted versus the CO2 selectivity. So then you actually have an undesired bioreaction, because then you're burning the methane. So the green data should be, let's say, as far as in the top right as possible. And for the CO2 selectivity should be, and that should be as low as possible today. So from these kind of plots, you can find the best catalyst. So the catalyst with the best selectivity with the lowest byproduct, for example, to CO2. Now you can do a similar study, and let's say for the same reaction, but with a completely different goal. So then you also have a completely different experiment. That's really a process optimization. So then you take a few catalysts, that you test them under different residence times. So here the x-axis in these, let's say, rainbow plots is the gas hourly space velocity. So the residence time of the gas, the methane in your reactor. And the y-axis is the temperature. So we change the temperature in the reactor. And then the color is again either C2 yield, so the more red, the higher the yield, or the CO2 yield, so that's the undesired product. So in this way, you can see where the most optimal reaction conditions are for this reaction, which are in this case at higher, around 820 degrees. That's actually at a low residence time. So you don't need to add, you shouldn't add your reactant too fast. So here we test many conditions with a few catalysts. Now there's a third category of, let's say, experiments where you really look at the catalyst preparation. So that is the example on the right. So there we do propane oxidation to acrylic acid. And there we have one catalyst made in 96 different ways. So it's the same combination of elements, but prepared in a different way. And then you see that after many tries, so initially the orange, sort of the brown orange circles show where we first started. And then after changing our catalyst synthesis, we came with the blue circle. So this is one catalyst composition with many synthesis methods. So these are three completely different ways in which we used our high throughput approach. So you should think in advance which of those three which of those three experiments you actually want to do. Okay, so this was our catalysis business unit. Now I move to Volta, which is our electrocatalysis platform for CO2 conversion, which I'm responsible for myself. And I chose this picture of the people because the person on the right, the guy, René Becker is his name, he's actually responsible for the technology that you will see later in the slide. So I want to give him the credits for that. So electrochemistry, and that's what we're working on in our Volta program, is about 10 times more efficient than photosynthesis. So here in the middle, you see photosynthesis. So from CO2 and water, plants can make very complex materials, for example, sugars. And as byproduct, they make oxygen. The efficiency of solar energy to complex materials is around 1%. Whereas if you go to electrochemistry, so in the middle at the bottom, Then this efficiency of CO2 and water to products is around 10%. And you don't make these nice complex materials that plants can make, such as sugars. You make very basic molecules. But actually, those basic molecules you can use to make, for example, fuels. And there, actually, this 10% is really important, this 10% difference in efficiency. Because if you want to make fuels, and then from biomass, you would need way too much land. But that's actually another story, so I shouldn't go into much detail there. So electrochemistry is very efficient, but that's at the top, bottom left. It's too expensive compared to fossil hydrogen or fossil fuels. It's about 3 to 5 times more expensive. And ways to solve that would actually be to develop new materials. For example, if you want to make hydrogen using proton exchange membranes, or PEM, then you need iridium to make the counter reaction oxygen. And iridium, there's for sure not enough iridium to do this, so we would need something else. If you want to create more value from this reaction, so not only make hydrogen, but also make another product at a counter electrode, you can use another reaction there, but then we need a new catalyst. So that's also a new material that needs to be developed. Or it would be ideal if we need less electricity to convert the CO2 in the electrochemical reaction. So also there we would need better catalysts. And so clearly a high throughput approach here would help to test many catalysts for different reactions, either to split water or to convert CO2. So what we did is we developed a high throughput setup to test electrocatalysts. So what you see here is on the left, let's say a wafer with 64 electrodes. On this wafer, we can put a gasket with flow fields, and this the wafer plus the gasket goes into a cell where we can flow the liquid through and apply the current to run the reaction. And then I go to the next slide. So here you see the results of a project that we did together with VSPARTICLE, with CEF, which is zero emission fuels. So on this wafer, VSPARTICLE has deposited an array of 64 different materials. So actually on the x-axis, the ratio of nickel and iron is varied. So at the left, there's 0% nickel and 100% iron. On the right, it's the other way around. And on the y-axis, we varied the deposition time. So the amount that VSPARTICLE, or the time that VSPARTICLE has deposited that particular ratio of metals, of nickel and iron. And then the graph on the right shows the results. So we have used those 64 catalysts for water splitting, in this case in an alkaline water splitter. So you use a sodium hydroxide solution, you use nickel iron electrodes, like we did here. And we measured the potential for each individual electrode. And in this case, the lower, the better. And the lower here means darker blue. So you see that, at least for this test, it seems that a high amount of iron works better at a longer deposition time. So this was really a test to see if this high throughput approach could work to find, or to at least to discriminate materials. And as you see, we can. So this is a very promising result to further optimize such a system. So actually, this already brings me to the end of my presentation. So I want to show you that high throughput approaches can really help you to find new materials, both in, let's say, conventional heterogeneous catalysis and in electrochemistry, which is a new emerging area. And that and we are developing new technologies for that, also together with VSPARTICLE. And that we really think that bringing companies together, that working with universities, can accelerate this development of new materials. So thank you.
Thank you, everyone. I hope everybody found this presentation insightful. Katarina is here with us. Katarina, would you like to introduce yourself a little bit to our audience?
Yeah, hello, my name is Katharina Weber and I'm working at VSPARTICLE for 3 years now in the R&D department. And I'm developing the nanomaterial printing technology that I have also used to prepare the experiment that Klaas van Schouten showed with the 3x3 matrix of the iron-nickel material catalyst screening.
Thank you so much, Katharina. I think we're ready to go to take some questions and answer them. Here comes the first one. For the nickel and iron electrocatalyst screening, how do you control the nickel to iron concentration?
Yeah, in this case, we had 2 generators. One was equipped with nickel and one with iron. And by setting them to different powers, we could control the ratio. So it works in a gas stream, and the bulk material is transformed into a nano aerosol. And one generator then has a nickel aerosol, and the other generator provides an iron aerosol. These 2 streams are combined and printed on to the substrate. And yeah, by controlling the power that the generators run on, we can also control the amount of nanoparticles that are generated, and thus vary the ratio quite quickly and easily.
Thank you. What is the effect of the deposition time on the material?
So we use a printing technology, and you can a bit imagine it like a 3D printer for plastic. And so the longer that you print on a dot, the more material you build up on that dot. And thus you can vary. If you print for a very short time, so a second, as in this experience for the shortest deposition time, you might only deposit a sub-monolayer of material. And when you print longer, you really build up a nice thick layer for our technique, up to a few microns thick.
Bingo. What materials can you deposit with the VSP technology?
So the materials that work with the spark ablation technique, that is what our generator is based on, that can work with every conductive material. So we can use pure elements that are metallic or semi-metallic, so silicon also works. But we can also use alloys and a combination of elements. The main the important property here is that it has to be conductive as it works with spark ablation.
Yeah. And now we are approaching, unfortunately, the last question of the session. I see we still have 2 unanswered questions, and we'll do a follow-up email to answer that. For the last question, how many different materials can be printed in order to get binary, ternary alloys? Could you give any suggestions?
So that depends on the number of generators, nanoparticle generators that you want to use. So in the experiment shown here, we use 2 generators, and thus you can combine 2 pure materials. However, you can also start from a bulk material that is not pure elemental, but is an alloy, or that is sintered. And in that way, you can have as many elements as you want in your base material. And then with a spark ablation technique, we can turn this into nanoparticles and print it on the substrate.
Thank you so much, Katharina, and thank you everyone for attending our session today. I hope to see you also in our future session on the 11th of March, when we will give a webinar about spark ablation. Until then, I wish everyone a good day, and we will follow up shortly with the answer for the remaining questions. Have a nice day and hope to see you here in the future. Bye-bye.